Hello everyone, I'm Paul and today we're solving problem 778, swim in rising water. This is a reasonably hard one and here I will show you how to solve this step by step. We are given a grid, so let's say we're given this, and this part might be confusing, but basically each number here represents some elevation or time. You can call this elevation, time, or elevation/time. It's basically the same. So for simplicity, we will say that these are seconds. We start from the source and let's say we're trying to access this neighbor. We have to wait 2 seconds to access this. We need to return the minimum time to reach the bottom right square. So we start from top left and we need to reach bottom right. For this example, we have 2 paths. We can go from 0 to 2 and from 2 to 3. The total time required to reach 3 with this path is 3. So we have one path which requires 3. The other path is we start here, we wait 1 second, we move here, we wait 2 more seconds and we can go here in 3 seconds. So we also get a 3 with this path and the minimum among these 2 paths is 3, so we return 3. If we are given this grid, here you can see the winner path and the required time for this is the maximum value in this path, which is 16. So we need to spend 16 seconds to use this path, and this is the minimum time required to reach this cell. So in this case we return 16. We need to return the minimum time to reach this last cell. And here, this is the winner path and the result is given by the maximum value in the winner path, which is 16. So maybe you're thinking about running a BFS from every cell as the source. So at some point you will use this as the source for a BFS. And remember that in BFS we move in circles. So from here we can go up, left, or down. We are checking every time that the neighbor is smaller or equal to the current value. So we can move here, and we can't move here. Now, we are checking if from this source we can reach this and these cells. And if we can, this means that this is the maximum value for a valid path. So we are keeping the minimum valid source and we can just return this. In this case, we return 16. Now, this is fine, but the problem is down here in the constraints. We know that n is smaller or equal to 50, and this approach requires a different BFS from every source, and this requires n to the power of 4 time complexity. And this is a lot, even for n smaller or equal to 50. So we need to think about something else, something more efficient. And the key here is to realize that we need to return the minimum maximum time to reach this point. So we can have a heap, and instead of running a different BFS from every cell, we start from the source. And we are visiting every neighbor, so we visit this and this, and every time we are keeping the maximum among the current value and the value for the neighbor. In this case, the maximum between 0 and 1 is 1, so we keep 1 here, and we add this to the heap. The same goes for this cell. The maximum between 0 and 24 is 24, so we keep 24 here, and this is no longer in the heap. We pop this. Now we have 2 elements in the heap and we can continue. Now we need to pop the next element, and remember that the first element in the heap is the smallest one. So we pop 1 and we need to visit this and these neighbors. And we repeat the same. We are keeping here the maximum between 2 and 1, which is 2, and here the maximum between 1 and 23 is 23. So we remove this and we continue. Now the next minimum element, the next value that we need to pop is 2, so we repeat the same process. So we continue and now we are here. We have these two neighbors, and here the maximum between 15 and 16 is 16, so we replace this with 16. Here the maximum between 16 and 20 is 20, so we keep 20 and we can pop this and continue. Now the next minimum value in the heap is this one, 16. So we are checking this neighbor first, and the maximum between 16 and 14 is 16, so we replace this with 16 and we keep 19 here. And we remove this from the heap and we add this. Here we do the same, we keep the maximum between 16 and 12 here, so we replace this with 16, and the maximum between 16 and 17 is 17, so we keep 17 here, we pop this and we continue. And once we reach this last cell, we return the corresponding time, which is 16. So with this approach, we are running only one BFS. We start from row 0, column 0, and we continue until we reach the destination. So with this in mind, let's go with the code. First we say n is the length of grid. Our heap will contain the source initially, so we add an array with grid 0, 0 and the coordinates for the source, row 0, column 0. And we will have a set to keep track of the cells that we have already seen. So this is a set, and this includes row 0, column 0 initially. Now while we have something in the heap, every time we pop 3 values, time, I and j. This is heap q, heap pop from h. And if we reach the last cell, we need to return the current t. So if I is n minus 1 and j is n minus 1, we just return t. Else we need to visit every neighbor, so for ni and j in I plus 1 j, I minus 1 j, I j plus 1, I j minus 1. First we are checking if we are inbounds, so if ni is more than 0, or j is more than 0, or ni is greater or equal to n, or j is greater or equal to n, or we have already seen this neighbor, so ni and j is seen, we continue. If we are still here, sin.add ni and j and heap q heap push into h. Remember, here we add a tuple and 3 values. The first one is the maximum between t and grid ni and j, and the second value is ni and nj. So we don't have to return anything here. At some point we reach the last cell and we return t. So this is the entire code. Now let's submit this and see if it works. As you can see, this works and it's very efficient. Heap operations, heap push and heap pop require log n time complexity, so overall time complexity here will be big O of n square, log n square, and space complexity will be big O of n square. So this is it for this problem. If you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.